After the Chicxulub asteroid struck Earth, life did not disappear immediately. During the first thousands of years of the Paleocene, the skies remained covered by silicate dust, ash, and soot from global wildfires. Some climate models suggest that global surface temperatures may have dropped by dozens of degrees Celsius within a relatively short time after the impact. Photosynthesis nearly collapsed, and food chains were severed at their roots. And when plants began to die, the giant creatures that had once dominated the planet died with them. Regions that had once been densely covered by Cretaceous vegetation were now reduced to black ash stretching all the way to the horizon. Then something strange appeared in the fossil record. Not giant trees or flowering plants, but ferns. Paleobotanists call this phenomenon the fern spike. The sudden explosion of fern spores in the fossil record immediately after the KPG mass extinction. In sediment layers across the world, fern spores appear in unusually high concentrations, suggesting that they were among the first organisms to cover the planet in green again after the catastrophe. Some studies indicate that ferns dominated many ecosystems for at least around 30,000 years after the impact. Why, in a world that once belonged to gigantic dinosaurs, were the first survivors small, almost primitive plants? It was precisely the simplicity of ferns that allowed them to endure. They reproduced by releasing millions of microscopic spores into the air. Life slowly began returning in its most primitive form. Microorganisms decomposed the bodies of giant creatures scattered across the planet. Fungi and bacteria restarted the carbon cycle. Plants emerged from the ash, and ecosystems rebuilt themselves layer by layer, slowly, like a planet learning how to breathe again. And within that ruined world, tiny creatures began surviving better than any giant species. Mammals of this era were, for the most part, only the size of modern mice or weasels. Studies of the KPG extinction suggest that small body size and flexible diets were two of the most important factors that allowed many mammals to survive the collapse of the global ecosystem. That was the moment when the age of mammals truly began. For more than 160 million years throughout the Mesozoic era, most mammals existed only as small, marginal creatures, hidden away and constrained by the giant reptiles that dominated every major ecosystem. During the Paleocene, the rate of mammalian diversification increased dramatically. Within only about 10 million years after the catastrophe, the average body size of many mammal groups expanded by dozens of times. One of the most remarkable groups was the pantodonts, the first truly giant mammals to emerge after the age of dinosaurs. They were not especially agile, nor particularly intelligent, yet their bodies kept growing larger and larger. Berry lambda is a striking example. This creature measured nearly 4 meters in length and weighed around 635 kilograms, with a low-slung body, powerful limbs, and a muscular tail that may have helped it balance while standing upright to pull down tree branches for food. In the ancient swamps, Coryphodon evolved along a different path. Weighing nearly half a ton, it lived a semi-aquatic lifestyle and fed on water plants. Fossilized teeth suggest it spent much of its time around rivers and lakes, much like modern hippos. Yet the brain of Coryphodon was astonishingly small compared to its body size, only a fraction of the brain volume seen in many mammals today. Then the first mammalian predators began to appear. Titanoides, one of the earliest large predators of the Paleogene, weighed around 136 kilograms and possessed unusually long canine teeth and powerful jaws. High in the trees, more agile species began developing hands better suited for gripping branches. Underground, burrowing species thrived as they adapted to escape predators and survive extreme temperatures. But while mammals were spreading across Earth, the planet itself was preparing to enter another crisis. One even stranger than before, around 56 million years ago. Earth began warming at a terrifying pace. And the Paleogene world was about to transform into a true planetary fever, an event scientists today call the PETM, the Paleocene-Eocene thermal maximum. Within only a few thousand years, the global average temperature rose by an additional 5 to 8 degrees Celsius. In many polar regions, the increase was even greater. And the terrifying part is that the cause may have come from carbon itself being released into the atmosphere on a massive scale. But where did all that carbon come from? Some hypotheses suggest that intense volcanic activity in the North Atlantic released enormous amounts of CO2 over long periods of time. Another hypothesis proposes that methane hydrates, vast, ice-like methane deposits buried beneath the seafloor, became unstable as temperatures increased, releasing gigantic quantities of methane into the oceans and atmosphere. And methane is a greenhouse gas dozens of times more powerful than CO2 in the short term. Once a chain reaction begins, an entire planet can be pulled into a runaway spiral of warming beyond control. Geochemical evidence suggests that somewhere between 3,000 and more than 7,000 gigatons of carbon may have been injected into Earth's climate system during the PETM. As Earth warmed, the ocean slowly began dying from within. Warm water holds less oxygen than cold water. Fossil studies suggest that around 30 to 50% of deep-sea foraminifera species became extinct during the PETM, making it one of the most severe deep ocean extinction events of the Cenozoic era. On land, life began migrating. Subtropical forests expanded toward higher latitudes. Primitive mammals appeared across North America, Europe, and Asia, almost simultaneously through ancient land bridges. But perhaps the strangest change involved body size itself. Many mammal species during the PETM became significantly smaller. Fossil evidence shows that early ancestors of modern horses, such as Cypheripus, reduced their body size by nearly 30%. In a hotter environment, smaller bodies dissipate heat more efficiently and require less energy to survive. The PETM reveals a terrifying truth. Earth does not need an asteroid to completely transform life. Once the climate moves beyond equilibrium, the planet itself can become something entirely different. Yet the paradox is that this extreme greenhouse world also opened the door to another biological explosion. As the Eocene began, Earth transformed into a gigantic living greenhouse where tropical forests spread nearly to the poles. Crocodiles lived in the Arctic, and a hot, humid atmosphere covered almost the entire planet. Earth during the Eocene, roughly 56 to 33.9 million years ago, was the hottest period of the Cenozoic era, a living greenhouse on a planetary scale. Global average temperatures are estimated to have been around 10 to 14 degrees Celsius higher than today. Atmospheric CO2 concentrations may have exceeded 1,000 parts per million at many points in time. Fossils discovered on Ellesmere Island in Canada reveal that around 50 million years ago, regions near what is now the Arctic Ocean once contained swamps, broadleaf forests, and even ancient relatives of crocodiles. This suggests that average temperatures in the polar regions during the Eocene may have ranged between 18 to 23 degrees Celsius, comparable to many modern subtropical regions. At this time, Earth resembled a gigantic climate machine powered by water vapor. The atmosphere held extraordinarily high humidity. Rain fell frequently, tropical forests stretched into latitudes never seen in modern history. And as temperatures continued rising, flowering plants began an explosion unlike anything before. Paleobiologists describe this as part of the flower revolution, a period when angiosperms, or flowering plants, expanded and restructured nearly every terrestrial ecosystem on Earth. Palm trees flourished across much of the world. Early ancestors of cacti began evolving water retention mechanisms to survive in localized hot, dry environments. Fossils of Archaeamphora, one of the oldest carnivorous plants ever discovered, suggest that Eocene vegetation had already begun developing remarkably specialized survival strategies. Flowers led to pollinating insects. Insects supported birds and fruit-eating animals. Forests became the densest biological networks to exist since the KPG mass extinction. And during the Paleogene, another evolutionary explosion was about to unfold, one happening on a much smaller scale, yet one that would influence the entire planet. If every large animal of the Eocene disappeared overnight, the forests might still continue functioning normally the next morning. But if insects vanished, the entire planet could collapse. During the Paleogene, as tropical forests spread across the world and flowering plants exploded in unprecedented numbers, another silent revolution was unfolding beneath the canopy. The explosion of insects. More than 500 Paleogene insect species have already been identified from fossils, and the true number was likely far greater. Beetles, ancient bees, ants, termites, flies, and especially weevils, plant-eating snout beetles, began diversifying at astonishing speed. Fossil studies show that the number of plant-feeding insect families increased dramatically alongside the expansion of flowering plants during the Eocene. Flowers changed to attract insects. Insects changed to exploit flowers more efficiently. And every small adaptation pushed biodiversity to expand exponentially. Eocene flowers were not simply plants. They were biological power stations. Nectar supplied sugar. Leaf-eating beetles forced plants to evolve chemical toxins for defense, and insects in turn evolved resistance to those toxins. It became a biological arms race that lasted millions of years. Termites decomposed cellulose from dead wood and fallen leaves, recycling carbon back into the soil and atmosphere. Ants formed some of the first highly organized societies, with clear divisions of labor between soldiers, workers, and queens. Some fossil evidence suggests that Paleogene ants had already developed coordinated group hunting behaviors, similar to many modern species. Creatures only a few millimeters long were building the first biological superorganizations on land. And then the nights of the Eocene truly became another world. Millions of insects glowed, hunted, mated, and pollinated simultaneously. The whole ecosystem functioned through creatures so small that many large mammals may have barely noticed they existed at all. While mammals were evolving to dominate the land, the final descendants of the dinosaurs had not disappeared. They were evolving in an entirely new direction, to the sky. Modern birds are the final descendants of theropod dinosaurs. But during the Paleogene, they were not yet the small creatures we know today. In a world where ecosystems were still rebuilding themselves, many birds rose to replace the roles once held by giant predators, becoming Earth's new versions of dinosaurs. One of the most haunting creatures of the early Paleogene was Gastornis, a bird standing roughly 1.8 to 2.1 meters tall and weighing more than 100 kilograms. Its immensely powerful legs allowed it to move rapidly through the hot, humid forests of the Eocene, while its enormous beak, several centimeters thick, once led paleontologists to believe it was a top predator. Yet modern carbon isotope studies from fossilized enamel suggest that Gastornis may have primarily eaten tough vegetation or followed a more omnivorous diet rather than hunting prey. Why would evolution create such a gigantic beak for a species that was not a specialized predator? Perhaps after the mass extinction, nature was no longer following the old rules. Meanwhile, in the isolated southern hemisphere, the first ancestors of the terror birds began to emerge. They belong to the group Phorusrhacidae, flightless birds capable of running at extraordinary speeds, with long necks, massive heads, and hooked beaks shaped like battle axes. Some later species grew taller than 3 meters and became the dominant predators of South America for tens of millions of years. The terrifying part is that they did not need claws like Velociraptor or jaws like Tyrannosaurus. A single strike from a beak weighing several kilograms could generate enough force to shatter the bones of prey. But it was not only the skies or the land that were changing. The Paleogene oceans also witnessed the rise of another surviving dinosaur lineage, ancient penguins. Waimanu, which lived around 61 million years ago in New Zealand, was one of the oldest penguins ever discovered. Standing nearly 0.9 meters tall, it already used its wings like paddles to fly underwater. A few million years later came Kumimanu, a true monster of the seas, nearly 1.8 meters tall and weighing more than 100 kilograms. Imagine a creature resembling a modern penguin, yet standing shoulder-high to an adult human, diving hundreds of meters into dark ocean depths to hunt ancient fish and squid. What is astonishing is that while mammals were accelerating their evolution on land, birds were also quietly taking over the remaining ecological niches. Nature did not simply recover after the KPG catastrophe. It completely rebuilt the world using entirely new designs. And then, as birds continued dominating the Paleogene skies, evolution on land began creating creatures even stranger still. Gigantic mammalian monsters that looked as though they had come from another planet. After the dinosaurs disappeared, the Paleogene opened one of the strangest chapters in the history of evolution. A time when nature began experimenting with biological designs that had never existed before. With the reptilian titans no longer dominating the land, mammals began expanding in size at astonishing speed. Creatures with enormous skulls, grotesque claws, giant hollow horns, and bodies that looked as though they had been assembled from multiple different species. The Paleogene resembled a gigantic laboratory of life. And the first monsters of the age of mammals were born. One of the most controversial names is Andrewsarchus, a predator that lived roughly 45 to 36 million years ago in what is now Mongolia. Based on body proportions, Andrewsarchus may have reached around 5 meters in length and weighed close to a ton. Its jaws were enormous, equipped with thick, crushing teeth similar to scavengers, as well as sharp teeth capable of tearing flesh. Then there was Entelodon, a creature often nicknamed the Hell Pig. Even though it was not truly a pig, some Entelodon species exceeded 2 meters in length, stood nearly 1.8 meters tall at the shoulder, and possessed abnormally thick skulls. Fossil bite marks suggest they frequently fought one another using their jaws. Their immensely powerful bite force could crush bone, while their long legs allowed them to run quickly across the expanding open landscapes of the late Eocene. But not every Paleogene monster was a hunter. Chalicotherium looked like a bizarre evolutionary mistake. It had the body shape of a horse, yet its elongated front limbs ended in enormous curved claws stretching tens of centimeters long. Instead of using those claws to hunt prey, it used them to pull branches downward and feed on leaves, almost like a gigantic sloth walking on its knuckles. It is proof that evolution does not move toward perfection, but toward efficiency within specific environments. Meanwhile, Arsinoitherium made the Paleogene feel like an alien world. It measured around 3.5 meters long, weighed more than 2 tons, and carried 2 massive hollow horns on its head. They dominated many Eocene plains before climate change eventually drove them to extinction. The most terrifying part was not their size, but the speed of their evolution. In only about 10 to 15 million years after the KPG mass extinction, mammals evolved from tiny creatures living in darkness into gigantic rulers of the planet. The Paleogene reveals just how violently evolution can accelerate once ecosystems are completely shattered. But while these mammalian monsters were conquering the land, another branch of mammals was undergoing an even more extraordinary transformation, abandoning the land entirely to return to the oceans. And from small, river-dwelling creatures, they would eventually evolve into Earth's very first whales. Around 60 to 50 million years ago, global ocean temperatures were approximately 8 to 12 degrees Celsius warmer than they are today. Many deep ocean regions were almost entirely free of polar ice that would normally help cool and circulate the waters. This created nutrient-rich but oxygen-poor deep seas, the ideal environment for large predators to evolve and thrive. Marine food chains began restructuring completely. One of the earliest rulers was Otodus, the ancient ancestor of Megalodon. Fossilized teeth suggest it may have reached lengths of around 8 to 9 meters during the early Paleogene, with jaws powerful enough to slice through the flesh of primitive whales. Otodus' teeth measured nearly 10 centimeters long, with edges as sharp as blades, and they were continuously replaced throughout the shark's lifetime. Modern studies estimate that large sharks can replace more than 20,000 teeth during their lives. The Paleogene oceans did not merely contain predators, they contained biological weapon systems, capable of endlessly regenerating themselves. But the more terrifying transformation lay within the structure of marine ecosystems themselves. Before the KPG extinction, giant marine reptiles occupied the highest predatory levels of the oceans. In estuaries and coastal swamps, Thoracosaurus emerged like a ghost left behind from the age of ancient reptiles. It measured roughly 7 to 9 meters long, with a narrow, elongated snout resembling that of a modern gharial, specialized for hunting fish in murky waters. Some fossil evidence suggests this species survived the KPG extinction event itself, meaning it witnessed the collapse of the dinosaur world and continued living into the new one that followed. And then, around 58 million years ago, within the hot, humid rainforests of South America, the largest snake ever known began moving through the swamps of the Paleocene. Titanoboa stretched approximately 12.8 to 14 meters long, weighed more than a ton, and possessed a body diameter approaching 0.9 meters. The crushing force generated by its immense muscles alone was enough to stop the blood circulation of its prey within seconds. The size of Titanoboa also revealed something else. Earth's climate at the time was vastly hotter than today. But the Paleogene was terrifying not only because of what could be seen, it was also terrifying because of what remained hidden in the darkness. While ancient whales hunted through the oceans and multi-ton predators roamed across the land, a small group of creatures with forward-facing eyes was quietly developing the most dangerous weapon in the history of life, the brain. And almost no organism on Earth at that time could have imagined that these animals, weighing less than a few hundred grams, would one day reshape the entire planet tens of millions of years later. Around 66 to 63 million years ago, the first primitive primates began appearing after the KPG extinction event. One of the earliest known candidates was Purgatorius, a tiny creature measuring only around 10 to 15 centimeters in body length and weighing roughly 100 grams. It possessed flexible feet capable of gripping branches, fingernails, instead of sharp claws on some digits, and depth perception superior to many mammals of its time. In a world of dense tropical forests, where the distance between life and death could be nothing more than a single miscalculated leap, the ability to judge space accurately became an enormous evolutionary advantage. Fossil studies from North America, Greenland, and Europe suggest that by the beginning of the Eocene, primates had spread rapidly thanks to the globally warm climate. Tailhardina, an early primate living around 56 million years ago, may have migrated across ancient land bridges, connecting continents as Earth's temperatures surged during the PETM. What is astonishing is that their tiny skulls already showed expansion in brain regions associated with vision and motor coordination. Then came Notharctus, which lived around 50 million years ago in North America. It measured nearly 60 centimeters long, possessed a long tail for balance, and had large forward-facing eyes. The structure of its arm bones suggests it could grip branches extremely well, resembling primitive versions of modern apes. By today's standards, the brain of Notharctus was still small, yet the ratio of brain size to body size had already increased significantly compared to many other Paleogene mammals. And here, a silent revolution truly began. Tiny changes, almost invisible from one generation to the next, yet continuing across tens of millions of years. Humans did not emerge by dominating the Paleogene. On the contrary, our ancestors survived by avoiding attention in a world filled with monsters. Toward the end of the Paleogene, global temperatures gradually declined, tropical forests retreated, grasslands expanded, and Antarctica began forming permanent ice for the first time in tens of millions of years. A greenhouse planet was transforming into a colder world, and many of the giant creatures that once dominated the Paleogene would not adapt quickly enough to survive the new era that was coming. After the dinosaurs vanished, Earth entered an era in which size, strength, and biological violence became the new rules of survival. The clearest symbol of the post-dinosaur Earth was Titanoboa, a creature that needed neither venom nor great speed, only mass and heat. With an estimated length of 12.8 to 15.2 meters, and a weight exceeding 1,300 kilograms, Titanoboa was the largest snake that ever lived. But what mattered was not size alone. Titanoboa could exist only in the extremely hot Paleocene climate, when global average temperatures were estimated to be 6 to 8 degrees Celsius higher than today. Its enormous body was a direct consequence of an overheated Earth, one in which heat exchange, energy, metabolism, and physiology were all pushed to their limits. They were the logical product of their environment, tropical forests stretching almost to the poles, atmospheric carbon dioxide levels far higher than in the pre-industrial era, and cold-blooded animals no longer constrained by temperature. Size was no longer a burden, it became an absolute advantage. Greater hunting efficiency, fewer predators, and cold, unquestioned dominance of the food chain. But Titanoboa was not alone in South America. A continent isolated for tens of millions of years. Another group of creatures rose to fill the void left by the dinosaurs. The terror birds. These giant predatory birds stood 2.5 to 3 meters tall, could not fly, but ran fast, armed with curved, blade-sharp beaks. Without wings, they evolved powerful legs and precise predatory vision. In a world lacking large competing carnivores, terror birds became the undisputed rulers of the land. What is truly frightening is not any single species, but the broader evolutionary trend. Violence did not disappear with the dinosaurs. It only changed its form. Earth merely optimized survival under extreme conditions. And in the Paleogene, those conditions favored creatures that could exploit abundant resources to grow enormous. In a world where snakes could swallow crocodiles whole, where birds could chase down and kill any mammal smaller than themselves, intelligence alone was not an advantage. Size was power. The dinosaurs were gone. The new creatures no longer looked ancient. But they were dangerous in a different way, quieter, more flexible, and finely tuned for a planet heating up at a relentless pace. And if size and strength rule this world, what happens when a smaller, weaker species appears? One that knows how to cooperate and to learn. After the first monsters established the new rules of survival, Earth did not stop. It pushed life even further, entering a phase in which size was not merely an advantage, but an evolutionary weapon. This was the age of megafauna, an era in which creatures did not grow large to impress, but to survive on an unforgiving planet. Across the frozen grasslands and open forests of the Pleistocene, mammoths stood over 3.4 meters at the shoulder and weighed as much as 6 to 8 tons. Their long, curved tusks were not just tools for digging through snow to find food, but also weapons of defense against other massive predators. Here, size meant the ability to retain heat, store energy, and endure winters that lasted tens of thousands of years. But megafauna were not just gentle giants. Megatherium, the giant ground sloth of South America, could reach 6 meters when standing upright and weigh more than 4 tons. With its long claws and enormous muscles, it was far from a passive plant eater. Evidence suggests Megatherium was powerful enough to defend itself against large predators, turning sheer size into a living shield. Elsewhere, Glyptodon, a giant relative of the armadillo, carried a true biological fortress, a thick, rock-hard shell of bone that could weigh up to 1,000 kilograms. When it curled into a ball, Glyptodon was nearly invulnerable. On isolated Australia, Diprotodon, the largest marsupial that ever lived, reached 2.5 to 3 tons. It dominated its ecological niche simply by being bigger than everything else. On dry plains, size allowed it to travel farther for water and food, while few creatures dared to challenge it. And then there was one creature that forced every idea of the ultimate predator to be rewritten: Megalodon. In the oceans, where greater size means greater control over energy, Megalodon reached an estimated 18 to 20 meters in length, with teeth up to 18 centimeters long. Biomechanical models suggest its bite force ranged from 108,000 to 182,000 newtons, enough to crush the skull of a large whale in a single strike. What matters most is this: megafauna did not appear by chance. They were the result of 3 converging conditions. First, the extinction of the dinosaurs removed the largest ecological competitors. Second, abundant resources, lush vegetation, and biomass-rich oceans allowed massive bodies to sustain high metabolic demands. Third, evolutionary pressure favored larger individuals. Fewer predators, longer lives, and more efficient reproduction. The age of megafauna was therefore both the peak and the limit of one evolutionary strategy. Earth had tested maximum size, and for a time it worked until the conditions changed. At the edge of this world of giants, a smaller, weaker, but more flexible species began to appear. It had no teeth like megalodons, no armor like glyptodons, no weight like a mammoth's. What it possessed instead was an adaptive brain, skillful hands, and the ability to learn, because when Earth was ruled by giants, the arrival of humans was not a moment of victory. It was simply another experiment in evolution. Early primates emerged in Africa about 6 to 7 million years ago, with no long fangs, no claws, no exceptional speed, and no great strength. What they did have were grasping hands with opposable thumbs that allowed them to hold, rotate, and control objects. The first hominins, such as Australopithecus afarensis, stood less than 1.5 meters tall and weighed only 30 to 45 kilograms, making them painfully fragile among giant predators. They did not hunt large prey. They scavenged, gathered, and hid. Fossil evidence shows that many individuals were eaten by saber-toothed cats, prehistoric hyenas, and even giant eagles. Change came only when the brain began to grow faster than the body. About 2.5 million years ago, the brain volume of Homo habilis increased to around 600 to 700 cubic centimeters, compared with under 500 cubic centimeters in earlier primates. A larger brain allowed short-term planning, spatial memory, and, most importantly, the ability to learn from failure. Stone tools did not appear to establish dominance, but to compensate for biological weakness. The crude Oldowan flakes did not turn humans into apex predators. Fire, brought under stable control about 400,000 to 500,000 years ago, drove predators away, extended activity into the night, and transformed hard-to-digest food into easily absorbed energy. Fire did not make humans stronger than megafauna, but it kept them from being wiped out. What matters is this: humans did not evolve alone. Many parallel human branches existed, and most of them failed. Homo neanderthalensis, powerfully built and well adapted to cold climates, survived for hundreds of thousands of years in Europe. Denisovans left genetic traces, but vanished without clear cultural remains. Homo floresiensis, the hobbit humans less than 1.1 meters tall, survived on the island of Flores through small size and energy efficiency. Evolution tested many options. Modern humans, Homo sapiens, are not superior in strength, speed, or size. Their advantage lies in social flexibility. Early language allowed information to be shared beyond a single individual. And even though the dinosaurs are gone, and even though humans have appeared, Earth has never become a safe place. This planet remains a machine of constant change, always ready to rewrite the rules of survival. Throughout the Paleogene and Neogene, Earth's climate fell into a state of instability that lasted tens of millions of years. After the extinction shock at the end of the Cretaceous, global temperatures did not stabilize. They swung wildly from extreme greenhouse phases to deep cooling events. During the Paleocene-Eocene thermal maximum, or PETM, about 56 million years ago, average global temperatures rose by 5 to 8 degrees Celsius in just a few thousand years. A climate shock powerful enough to restructure the entire biosphere. Ecosystems barely had time to recover before being forced to adapt once again. In such an environment, life was not only confronting predators, but the planet itself. High temperatures caused rainforests to spread, but they came with crushing humidity, dense parasites, and thriving disease, causing microorganisms. On land, predators constantly changed form. Saber-toothed cats, giant hyenas, and the short-faced bear, Arctodus simus, which could stand up to 1.8 meters at the shoulder on all fours, became the nightmare of every smaller creature. There was no stable top of the food chain, only brief periods of calm before a new predator emerged and shattered the balance. Tectonic activity continued to rearrange the continents, raising mountains, forming plateaus, and opening new climate corridors. The uplift of the Himalayas during the Neogene did not just reshape the land. It altered atmospheric circulation, helped trigger monsoon systems, and pushed the planet toward global cooling. This set the stage for the Pleistocene Ice Age, which began about 2.6 million years ago, with repeating glacial and interglacial cycles every 41,000 to 100,000 years. In this world, human survival strategies were not built on individual strength, but on social organization. Tribes formed not out of idealism, but because living alone meant dying faster. Each time the climate shifted, each time the environment transformed, the planet was not attacking life. It was simply obeying its own physical and chemical laws. Life either adapted or it disappeared. So when we look back at Earth after the dinosaurs, we do not see a paradise waiting for humans, but a battlefield that lasted tens of millions of years, where only the most flexible survival strategies endured long enough to leave a trace. Humans are a product of that world, not absolute winners, but relentless survivors. And if Earth has been this way before, what triggered it all? To answer that, we must turn back time to the moment when this planet was truly reset. Turning back the clock 66 million years, Earth had no idea it was approaching a moment that would decide the fate of all life. There were no warnings in the climate, no long chains of earthquakes, no biological alarms. There was only a single cold object moving through the darkness of the solar system. And when it struck Earth, every old rule of biology was instantly erased. That object was an asteroid estimated to be 10 to 15 kilometers in diameter, about the length of an entire major city. It slammed into Earth at roughly 64,000 kilometers per hour, nearly 20 times faster than a rifle bullet. The energy released by the Chicxulub impact has been estimated as equivalent to more than 10 billion Hiroshima atomic bombs exploding at once. But even that number is only a metaphor. In reality, this was an event beyond any human scale. In less than a few seconds, the crust of Earth in what is now the Yucatan Peninsula was compressed, melted, and almost completely vaporized. The Chicxulub crater, about 180 kilometers wide and nearly 20 kilometers deep, is not just a geological scar. It is a boundary between two biological worlds. Under the extreme pressure and temperature of the impact, sulfur-rich limestone in the region was vaporized and blasted into the atmosphere. This would become one of the most important factors driving Earth into the dark age that followed. Shock waves raced across the planet at supersonic speeds, triggering global earthquakes estimated to exceed magnitude 10. No continent was spared. Volcanoes in many regions were jolted into greater activity, pouring even more gas and ash into an already chaotic sky. The impact itself ended in minutes, but its consequences were only beginning. In the first few hours, wildfires erupted on a global scale as trillions of red-hot fragments from the impact re-entered the atmosphere and rained down across Earth's surface. The heat was intense enough to ignite biomass across most continents. From tropical rainforests to northern conifer forests, forests that had endured for tens of millions of years vanished in just a few days. At the same time, tsunamis more than 100 meters high swept across the oceans, their impact energy powerful enough to generate waves that traveled around the globe, devastating coastlines thousands of kilometers away. The impact blasted about 15 trillion tons of dust and sulfur compounds into the atmosphere, mostly from the sulfate-rich rock layers of the Yucatan region. These particles did not fall back immediately. They remained suspended in the stratosphere, forming a dense veil that wrapped around the entire planet. Sunlight, the fundamental energy source for most life, was almost completely blocked. Climate models show that Earth entered a phase known as an impact winter, lasting from 10 to 15 years. Average global temperatures dropped by about 20 to 25 degrees Celsius in a short time. A shock that ecosystems had no ability to adapt to. This was not the slow climate shift of an ice age, but a sudden collapse in temperature. Species dependent on stable environments, especially large organisms, were pushed into a dead end. In this context, Earth became a gray, cold, and silent world. The familiar sounds of life, buzzing insects, bird calls, the movement of ecosystems, disappeared across vast regions. Not because every organism was dead, but because the density of life fell below the planet's threshold of perception. The most terrifying aspect of this period was biological disorientation. Millions of years of evolution had optimized organisms for a world with light, stable cycles, and continuous energy. When those conditions vanished, instinct was no longer an advantage. Size, strength, speed, traits that had ruled the Mesozoic world now became deadly burdens. Earth was no longer familiar to its own life. And in that world, about 75% of all species disappeared, as the planet's life support system collapsed. Plants were the first victims on a planetary scale, when sunlight was blocked for years. Photosynthesis nearly stopped across the globe. Land plants slowly died off, photosynthetic plankton in the oceans. The foundation of 90% of marine biomass collapsed. With the producers gone, the higher levels fell in a domino effect. Herbivores disappeared first. Carnivores followed. The largest species, which required the most energy, fell the fastest. Along with the darkness came acid rain. Sulfur dioxide in the atmosphere reacted with water vapor to form sulfuric acid, falling to the surface as corrosive rain. The oceans rapidly became acidic, making it impossible for calcium-shelled organisms such as ammonites, corals, and many kinds of plankton to survive. The seas, the planet's greatest source of life, turned into a hostile environment. Unlike anything before the fossil record at the KPG, Cretaceous-Paleogene, boundary shows that about 75% of Earth's species went extinct. This number is not a subjective guess. It is supported by multidisciplinary evidence. Stratigraphy, geochemistry, paleontology, and climate modeling. Notably, extinction was not random. It followed a pattern. Larger species died first. Specialists died faster. Organisms dependent on stable environments had no way back. The oceans, once thought of as a safe buffer, were not spared. Rapid acidification from acid rain and dissolved carbon dioxide prevented calcium-shelled organisms from forming their minerals. Ammonites, many corals, and calcareous plankton vanished en masse. When the base of the marine food chain collapsed, the large fish and marine reptiles that once dominated quietly disappeared from the geological record. Fossil pollen shows a sudden shift from trees to ferns and pioneer plants. Species that can sprout quickly under harsh conditions. This was not recovery. It was the signature of ruins. An ecosystem reverting to a primitive state. What makes this period truly frightening is not just how many species died, but how fast it happened. In Earth's history, many mass extinctions unfolded over hundreds of thousands to millions of years. This time, most of the collapse occurred within tens of thousands of years. And for many groups, within only a few thousand. Evolution, which needs time, could not keep up. Not all organisms require strong sunlight, long food chains, or stable environments. Some species live on leftovers, feed on carrion and debris, or can hibernate, slow their metabolism, and endure long periods of starvation. The fossil record preserves a few rare points of light in the darkness. Small mammals, birds, crocodiles, turtles, amphibians, and many groups of insects. They shared key traits: small size, low energy demands, short life cycles, and the ability to shift their way of life, not stronger, but more flexible. Crucially, ecosystems did not rebound right away after the extinction. It took millions of years for biodiversity to return to pre-impact levels. This reveals a cold truth: life does not bounce back like a switch. It rebuilds slowly through countless evolutionary experiments. Most failing, a few succeeding on a planetary scale. This period marked a restructuring of the biosphere. Empty ecological roles. Large herbivores, apex predators, remained unfilled. The world entered a relatively quiet age, where life survived, but did not yet dominate. And in that silence, new evolutionary lineages began to quietly take hold. When 75% of life vanished, Earth did not enter a glorious age. A planet still orbiting the sun, still holding oceans and continents, but with ecological roles left empty, food webs cut apart, and evolution forced to begin again from what remained. In those ashes, it was not the strongest that rose first, but the most unremarkable. Small size, short life cycles, and low energy demands, traits once seen as weaknesses, became absolute advantages in a world short on light and resources. Post-dinosaur mammals were no bigger than mice. They lived in burrows, ate whatever they could, were active at night, and could regulate their body temperature. A life-saving edge when the climate swung wildly. Fossils show that many species could hibernate, slowing their biological rhythms to survive long periods without food. As the giants went extinct, ecological gaps opened, and mammals began to fill them, step by slow but irreversible step. Birds were another group that made it through. But not all of them, only species that were small, agile in flight, and flexible in diet survived the early phase. Flight was more than a way to find food. It was an escape strategy from collapsing local environments. From these surviving branches, birds would later diversify again, reclaiming the skies once ruled by flying dinosaurs. Crocodiles and turtles, often called living fossils, endured thanks to their slow metabolisms and ability to withstand long periods without eating. Crocodiles can go months without food and thrive in murky, low-oxygen waters. Ironically, what looks like evolutionary outdatedness, little change over tens of millions of years, helped them survive a world in turmoil. Among plants, ferns became a symbol of renewal. Fossil pollen shows that after the impact, ferns exploded across the globe, creating what scientists call a fern spike, a clear geological signature of catastrophe. Ferns do not need flowers, do not rely on insect pollinators, and can spread by spores under harsh conditions. They do not build long-lasting forests, but they prepare the ground for more complex ecosystems to return. Mammals gradually became large herbivores, apex predators, and eventually beings capable of abstract thought. The end of the Cretaceous did not open the door to an instant paradise. It marked the beginning of a deeply wounded planet. For millions of years after the catastrophe, Earth functioned like a brutal laboratory. Skies choked with atmospheric dust, a climate swinging to extremes, and food chains completely shattered. It was at this razor-thin boundary between survival and extinction that the laws of evolution carried out a ruthless filtering. Control of the planet no longer belonged to the biggest giants, but shifted to the organisms most capable of flexible adaptation. The new world that replaced the age of dinosaurs emerged in the cold, quiet spaces of empty ecological niches. The persistence of mammals in this post-apocalyptic environment was not a historical accident, but a testament to life's resilience in the face of geological upheaval. And so, the extinction of the dinosaurs was not merely an ending. It was the starting point of a new biological order, a harsh but necessary chapter that ultimately cleared the path for the rise of humanity itself. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.